This is going to be a multi-part series on the modern theory, or some modern theory of AI voice. I'll be talking about token-based models and also continuous models. We see a lot of architectures across voice, a lot more than just the transformer as in LLMs. There are good reasons for that, such as voice being multimodal, which I want to talk about, the higher bitrate, as in there's a lot of information in voice compared to text. And I'm eventually going to go through the main classes of models and how I think the architectures are going to evolve from here. So for agenda in this one, I'm going to start. Let's do voice AI theory. Start by talking about the high bitrate in voice. The second thing I'll talk about is multimodality. And then I'm going to talk about tokens versus latents. Or versus, continuous. Discrete versus continuous might be another way to say it. And I'll talk through different models. So I'm going to talk through Piper, which is an example of a VITS model. Then I'll go to Style TTS2, which is an evolution of Piper or VITS. Then you have Kokoro, which is a modification of Style TTS. And then on the other hand, you have CSM or Orpheus. And then somewhat in the middle of these two, you have Quen TTS. And you also now have Voxtral TTS. And I'll lay those out a bit more clearly, but those two are somewhat in between tokens and continuous, although they're both really more token-based approaches than continuous. So for background, I'll say just a few quick things about high bitrate and multimodality. Starting with high bitrate, let me create a little space here. High bitrate. If I read text, for example, if I read the quick brown fox, I'm talking maybe 60, 120 words per minute. And that text, those text tokens are providing information at a certain rate per second. But when you have voice, not only are you communicating the information that's in the text, and the bitrate is a measure of the total information, so you have information here. In voice, you also, of course, have the tone or the emotion. You have the energy or the loudness. You have something called duration. I may, those two words, which happen also to be phonemes. A phoneme is a more acoustic representation of text. I can control the duration with which I say I and may. That's called duration. Models in the continuous space will often try to predict the duration of each phoneme, but I could vary that. So while text is just there's a token for that. It's a certain representation. I could say it slowly, quickly. I can control the durations within. Now these are all single syllable words, but I can control the duration between each of those syllables when I talk. So I have tone, emotion, energy, duration, prosody, which is a more broader statement about how I'm talking through these phonemes. And so the information I have is much greater than just the text. And that means I need, in my model, to communicate a lot more information per second. And if you think about a token-based model, it means I need many more tokens per second in order to represent that information, because I'm transmitting more information. And this makes it hard to use tokens for audio, because to have good representations, you need a lot of tokens per second. And if you need a lot of tokens per second, it's hard to keep up with the real rate of speech. And this is why a lot of the models in voice are smaller. And it would be nicer if you could have them larger from a quality perspective, but then you wouldn't be able to keep up with real-time speech. And this is another reason why the non-token type representations have persisted. It can be easier to represent voice in a continuous space than quantizing it into a tokenized space. And this is going to be a key theme. But suffice to say, a big challenge with voice models is that they have a lot more information per second than text. And so, you need to factor that into the architecture. The second thing I want to touch on is multimodality. And this can confusingly mean different things, because when we talk about multimodal models, we often mean text plus vision or text plus audio, and that is a correct interpretation. But what I mean here by multimodality is that if I have one sentence in text, it can be represented by many versions in voice. For example, I can just say the same sentence with different emotion, and that represents a different sound wave. But at an even deeper level, if I have a sentence like I said, she said, well, the audio version can even have different meanings. I could emphasize I said, she said, as opposed to someone else, or I could emphasize I said, she said, so it's her as opposed to someone else, or I could even say I said, she said, as opposed to some other verb. Maybe I yelled, or I didn't say, or I said. So you can see every text, such as this phrase here, can have very many meanings in audio, and it can also have very many representations emotionally, and the model needs to represent that. So if you just provide in text to a model, that's quite an incomplete description of what the meaning is. You probably need to inject as well what the reference speaker sounds like. You may also need to inject some indicator of what the broader meaning is, so the emphasis is put on the correct word. And this makes it significantly more difficult to build a voice model than just some kind of a text representation. So with these two things said, I'll quickly go through the classes of models that we see today. And it's nice maybe if I lay it out as a spectrum. On the right-hand side, we have token-based models. On the left-hand side, we have continuous-based models. If you look at some of the original continuous-based models, as I said, you have Piper, which is a variational autoencoder with adversarial training for speech. It doesn't actually match the acronym exactly. Don't worry if you don't understand that. I'll describe it later. Piper, to some degree, was improved then by doing Style TTS2, which then ended up being modified to provide the Kokoro representation, which is a very strong, very lifelike, emotive voice model that's very small as well. And then on the token side, you have CSM from Sesame, you have Orpheus. And then somewhat in the middle, because it uses tokens and continuous, is Quen TTS. And then even more towards continuous, you have the latest release, which is Style TTS, which uses tokens for the text part, but then continuous representations for the emotions. So this is kind of your hierarchy. It's interesting how, if you look at the trajectory of the field, we've gone something like maybe this over here, and now we're moving back in again. So this is the time lapse. And yeah, I'm not entirely sure if the direction is going to be more this way or this way. There are a lot of probably different applications. You'll find different directions to travel, and hopefully I'll describe and give a bit more color around where I think things will go. Also worth saying that broadly speaking, we have seen maybe better quality on this side. I think this is kind of the perception, better quality with token-based models, but I don't actually think that's necessarily the case. Whereas on this side, you kind of have speed and on-device. So this is kind of how people will look at it. If you run a model on CPU, you are probably running something more here. If you run a model on GPU, you are probably running something more here. But yeah, I think that's quite a generalization, and I'll hopefully give more color into that. So today in this video, I'm going to look at Piper, and it's a nice starting point because it's somewhat intuitive. What you'll find with a lot of these models over here, there's also a gradient around simplicity. So if you look at moving towards token-based models, they tend to be a bit more simple, whereas if you move towards continuous models, they tend to have a lot of components. So it makes them hard to understand what's happening. But this is broadly how things look.